Okay, third video here on differential equations, and we're looking at separable equations in the form of dy dx equals a function of x times a different function of y. Okay, so these are separable. I'm going to show the separable aspect. Now, in general, if we have dy dx equals f of x times g of y, we can separate them so that they take this form. Okay, so on one side we have integral of f of x dx, on the other side we have 1 over the integral, the integral of 1 over g of y dy, and note that the differential can sometimes sit up there on the numerator. So the differentials get split on opposite sides of the equal sign. We'll now have a look at two examples. The first one here is a general solution, and we have dy dx equals e to the 2x times 1 plus y squared. Okay, so this is the separation apart and that I was talking about, and so on one side we need to have things involving y, so what we can do is divide both sides by 1 plus y squared. And simultaneously we can multiply both sides by dx. You can see we have separation of variables now, y on the left side, x on the right hand side. What we do then is integrate both sides, the left hand side in regards to y. So it's like saying the integral of 1 over 1 plus y squared dy, and the integral of e to the 2x with regards to x. Okay, here we recall one of our results. So it's important to remember this form here. We have the integral of some constant a over a squared plus x squared dx. We have the arctan of x over a plus the constant. So on the left hand side, of course, our variable is y. Our value for a, and hence a squared, is 1. So we're going to have arctan on the left, and a being 1 is just arctan of x on 1, which is just arctan of x. And on the right hand side we've got half e to the 2x. Now the constants on the left and the right, and what we can do is just bundle them together as one constant. Okay, nice and easy. And so we have an expression, oh look what I've done, through habit, that should be a y. I was following the form too closely, wasn't I? Okay, left-hand variables are y. Okay, so we have to find an expression of y versus x. Okay, so y in terms of x, so we need to take the tan of both sides to undo the inverse tan. Essentially, we have half e to the 2x plus c in brackets. Okay, and that's a general solution. This one here is separable as well. We have a particular solution because we're given that extra information. So when x equals 0, y equals 1. So let's do this particular solution. So isolating, so we can get dy dx by itself. We have 6x squared y, take away y. And then we need to factorize in order to get the variable y by itself. That's important because separation of variables means x and y are free to move, and that means on the left hand side we'll have dy over y, and on the right hand side we'll have 6x squared minus 1 dx. And time to integrate both sides. Integrating both sides, we have integral dy over y, and we have the integral of 6x squared minus 1 dx. So our natural log of absolute y equals 2x cubed, I should say. 2x cubed minus x there, plus the constant. Okay, so now we know that using that information, when x is 0, y equals 1, so that gives us somewhere to go there. We know that log of 1 will equal c, basically, because these two terms here contain x, and hence they'll go to 0. Okay, and log of 1 equals 0, so c therefore equals 0. Okay, so we have log of y absolute equals 2x cubed minus x. Putting in exponential form, then we have e to the 2x cubed minus x. You might be asking, where did the modulus symbol, the absolute symbol, go there? Well, you see e to any power like that, that's going to be bigger than 0, okay? You might remember the exponential base functions, if they're not translated, have an asymptote at y equals 0, so they'll always be positive, so we don't need the modulus sign. So there's our particular solution.